What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 3, Section 4, Composition of Functions. Let's do it. How does one find the domain of the quotient of two functions, f and g? All right, so there's a couple ways to go about this. And by the way, when we're talking about domain of functions, really we're talking about two particular things that are going to be problematic. Number one, any place where you're going to be dividing by 0, that's going to be an issue. And also, taking the square root of a negative number. When you do that, you're out of the real number plane, so that would be a domain restriction as well. And when I say square root of a negative, this isn't just limited to square roots. It's also limited to fourth roots or sixth roots, anything where it's going to be an even index, because taking an even index root of a negative number is going to give you an imaginary solution. So the first thing you're going to do is you're going to figure out what the domain restrictions are of f in particular. Then you're going to find the domain restrictions of g in particular. So that's going to give you the initial domain restrictions, and you're going to kind of combine them. Whatever is restricted from f and restricted from g, that's going to comprise your domain restrictions. But then there's one other exception you have to look out for. Since it's a quotient of two functions, you also have to look for whenever g is going to equal 0, because you can't divide by 0 as we mentioned up here. So even if g in and of itself ends up being 0, that's not going to work because it's going to be f divided by 0. So that's a restriction as well. That's how you do it. Boom, done. If the order is reversed when composing two functions, can the result ever be the same as the answer in the original order of the composition? So this is absolutely possible. This actually happens in particular when two functions are inverses of each other. It doesn't always happen, but I'll give you an example where it will happen. So for example, if we have a function f of x equals x plus 2 and g of x equals x minus 2. Okay, these are actually inverse functions. Now, check this out. If I take f of g of x, and this notation is equivalent to f of g like that, the fog, it looks like fog, but it's f composed with g inside of it. So that would be taking this function and plugging it into this guy for that x. So it's got x minus 2 replaces the x plus 2. This is going to simplify, combine the negative 2 and the 2 to a x, because those will cancel out. Now we'll do it the other way, g of f of x. Now we're taking this guy and plugging it in for this x. So I replace the x with x plus 2, and then again minus 2. Once again, they cancel out, and it equals x. So they both get the same result, and by the way, they are inverses of each other. Boom, done. For the following exercises, determine the domain of each function in interval notation. So check this out. We're trying to get the domain for this, 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 and this. So let's first add these two functions together, right? We're adding f and g. So it's x squared plus 2x plus 6 minus x squared. Check it out. Cancel, cancel, right? Positive and negative x squared. So we end up with 2x plus 6. Now, are there any problems with x's? Like, is there anywhere we're going to get an even index of a negative or dividing by 0? No, it's a line. It's a linear equation. There's no domain restrictions, which means the domain is all real numbers, aka negative infinity to infinity. What about f minus g? So that's x squared plus 2x minus g of x, and we'll put it in parentheses, which would be 6 minus x squared. So we're going to distribute that negative. We got x squared plus 2x minus 6 plus x squared. Double negatives cancel out. So then we combine like terms. That's x squared plus x squared is 2x squared plus 2x minus 6. So once again, there's nothing here that I'm going to plug in that's going to give me an issue like a square root of a negative or dividing by 0. So once again, domain is all real numbers, aka negative infinity to infinity. Here we have f times g. I'm just going to need a little bit more room, so we're going to do it up top. So f is x squared plus 2x, and g of x is 6 minus x squared. So we're going to FOIL. So x squared times 6 is going to be 6x squared. That's these two guys. Then we're going to multiply these guys. That's minus x to the 4th. Then we're going to multiply these guys. That's plus 12x. And then we're going to multiply these guys. That's negative 2x cubed. Okay, so now again, I can put this in standard form, and why not? So it's x to the 4th negative, right? Because there's a minus in front, minus 2x cubed plus 6x squared plus 12x. Now, I didn't need to do that. It doesn't really matter when we're talking about domain, but why not? Just to show you the nice standard form where we got the highest degree first and then kind of trickling down. But the main thing to note is there's nothing that I can plug in that will create an issue, aka dividing by 0 or taking a square root or a fourth root of a negative. So once again, my domain is all real numbers, aka from negative infinity to infinity, boom, done. And last but not least, we got the quotient, okay? So I'll put it over here so we have a little more room. F over g. So I'm literally going to write that as x squared plus 2x over 6 minus x squared. And there's nothing we can really combine or simplify. So we're just going to look at this. Now, the numerator, all's fair game. We can plug in whatever we want. But the denominator, we got to be careful because we can't be dividing by 0. So basically what we're looking at is whenever 6 minus x squared, let's put it up here. Whenever 6 minus x squared is going to equal 0, that's going to be a problem. And there's two values that if we square it are going to make this go to 0, right? Because we want 6 minus 6 to give us 0. So the two values would be the square root of 6 and the negative square root of 6, right? If I plugged in both of those into x squared, we get 6 minus 6, 6 minus 6, that gives us 0. So those are the domain restrictions. These are the values that x cannot be. So we're starting at negative infinity, going up to and excluding negative rad 6, union, picking up at negative rad 6 up to positive rad 6. And then I just moved that up, made it a little smaller. And then union, we got to finish it off from rad 6 out to infinity. So this shows the viable domain. It's just excluding that negative rad 6 and the positive rad 6. Boom, done. Given f and g, find f plus g, f minus g, f times g, and f over g. And then once again, we're going to have to find the domain for each of these. So first, we're going to start with f plus g, aka just adding these two functions together like so. Boom. Now, if I want to consolidate and simplify a little bit, let's get all of these over a common denominator. So I'm going to put this over 1 and multiply the top and bottom by 2x. So as we distribute across the top, we get 4x to the third power, right? X times x squared is x cubed, plus 2x times 4x, which is 8x squared. And then this is already over 2x, so I'm just going to merge it together, plus 1. And now everything is over 2x. So that looks really good. Now we're talking about domain, right? Again, the numerator is good to go. It's a nice polynomial. You can plug in whatever you want. But that denominator, we can't have it go to 0. And it would go to 0 when x is 0, right? So the domain is everything but 0. Negative infinity up to 0 excluded. That's why we have the nice curved parentheses, union, and then picking up right after 0. All the way to infinity, boom, done. So here we're taking the difference of the two functions. It's almost equivalent to the sum, except I'm going to replace this plus with a minus. And once again, to get common denominators, just to simplify, even though this is essentially sufficient, we can multiply the top and bottom by 2x like so. Now as we distribute across, we have 4x cubed plus 8x squared. And again here, now it's minus 1 instead of plus 1. So minus 1 over 2x. So it's pretty similar. It's just a minus instead of a plus. Now, if we're talking about the domain restrictions, again, it's going to be when the bottom zeroes out, right? Because we can't divide by 0. So that's going to be everything but 0. So the domain is actually going to be the same. We're going to have from negative infinity to 0, curved parentheses because we're excluding 0, picking back up at 0, going to positive infinity, boom, done. Next, we have the product of f times g, so it's 2x squared plus 4x times 1 over 2x. So as we distribute like so and simplify, we're going to end up with 2x squared over 2x plus 4x over 2x. Now this is interesting because we can simplify this, right? The 2's cancel out. We got x squared over x, which simplifies to x. And we got 4 over 2 that cancels out to 2 over 1. And the x's cancel out completely. And we have this x plus 2. So you might look at this and be like, well, that's a polynomial x plus 2. And it's a linear equation. There's no domain restrictions, but we actually have to go back to before we canceled out the x's in the denominator. We still have to think about that original form when thinking about domain restrictions, because once again, even though it's simplified to this, dividing by 0 at this stage would still be out of the realm of real numbers. So what we're going to do is we're going to once again say 0 is out, and the domain, just like the above, is negative infinity to 0, excluding 0, picking back up after 0, going to infinity, boom, done. Last but not least, we have f divided by g, so we have 2x squared plus 4x divided by 1 over 2x, which is g. Now, this is dividing a fraction, so it's like multiplying by the reciprocal of that fraction, so I could rewrite this simplified as 2x squared plus 4x times the reciprocal of this, which would be 2x over 1, or just 2x. And once again, we distribute to simplify this product, and we get 4x to the third plus 8x squared. And just like the last one, you might think, all right, we've got a domain of all real numbers because it's a polynomial, but we have to remember we were originally dividing by this, which means, once again, this denominator cannot equal 0, and this denominator of that secondary fraction can equal 0. When is it going to equal 0? When x is 0. So once again, for my domain, we've got negative infinity to 0, excluding 0, picking back up after 0 to infinity, boom, done. So once again, we're going to start with f plus g, and that is simply 3x squared plus square root of x minus 5. There's really nothing we can simplify here, so we're good to go in this respect. Now, we're not dividing by anything, so we don't have to worry about dividing by 0, but we cannot take the square root of a negative. So this portion under the radical must be greater than or equal to 0, right? 0 is okay. Positives are okay, negatives would be a domain restriction. So to simplify this, that gives us our domain. X has to be greater than or equal to 5 by adding 5 to the other side. So we can represent that in interval notation as starting at 5, including 5. That's why we have the square bracket. If it was just greater than, we'd have a curved parentheses. And then going all the way up to infinity, boom, done. Now we take the difference, and once again, there's no real simplification here, so we're taking the difference. And we've got that same boundary, right? The radical cannot go to a negative. So really, our domain here is the exact same. We're going from 5 inclusive all the way to infinity, done. Next, we got the product. So the product is 3x squared times radical x minus 5. Nothing to really simplify here. And again, we're bounded by that same limitation. We can't take a radical of a negative. So my domain, once again, is from 5 to infinity. Last but not least, we got f over g. We're just going to throw 3x squared over radical x minus 5. So this is interesting because we still have a radical, still can't be negative. So we know that, again, at a minimum, we've got to be from 5 to infinity. But there's a little difference here. This also can't equal 0 now because it's in the denominator. So we can't divide by 0. So it's all of this, plus now we have to exclude 5 as well, right? So a way to think about this is x has to not only be greater than or equal to, x minus 5 has to not only be greater than or equal to 0, it actually has to be greater than 0 because now 0 is out of the mix. So we add 5 to both sides, x is greater than 5. So it's almost the same as these domains, except we don't include 5, so a curved parentheses to infinity, boom, done. So for this question here, we've got f of x equals 2x squared plus 1 and g of x equals 3x minus 5. And we're going to go through each of the parts. So when we've got f of g of 2, what I'm going to do is I'm going to start inside first. I'm going to take 2 and I'm going to plug it into g of x. So that's 3 times 2 minus 5. 3 times 2 is 6 minus 5 is 1. Then I take that 1 and I plug it into f of x. So it would be 2 times 1 squared plus 1. 1 squared is 1 times 2 is 2 plus 1 is 3. So part A is 3. Now for part B, we're going to plug g of x into f of x. So f of x is currently 2 times x squared plus 1. And I'm leaving the x blank because when we plug a function into another function, we replace all instances of x with that function. So I'm just going to slide 3x minus 5, which is g of x, into the x spot. And since the book leaves it like this, not simplifying, we're going to leave it like this. Boom, done. Now for part C, we're taking g of f of x. So what we're doing is we're taking f of x, which is 2x squared plus 1, and we're plugging it into g of x. So I'm replacing my x in g of x with an open parentheses, and then I'm sliding in f of x, which is 2x squared plus 1. Now, they did simplify it in the book here, so let's do that as well. We're going to distribute. We got 6x squared plus 3 minus 5. 3 minus 5 is negative 2. So we end up with 6x squared minus 2. Boom, done. Next, for part D, we've got g of x. So I'm going to take my g of x function, which is 3 times x minus 5, and I'm plugging g of x into itself. So every instance of x, I just replace it with g of x, which is this. And then to simplify, I'm going to distribute. We got 9x minus 15 minus 5, combined like terms, negative 15 and negative 5. Make negative 20, so 9x minus 20. Last but not least, we got f of negative 2, so I'm going to rewrite it like so. And we're going to start inside out. So first I'm going to plug negative 2 into f of x, so that is 2 times negative 2 squared plus 1. Negative 2 squared is 4. 4 times 2 is 8, plus 1 is 9. So since that inside part is 9, now we're taking f of 9. So we're plugging 9 into f of x, which is 2 times 9 squared plus 1. 9 squared is 81. 81 times 2 is 162 plus 1 is a final answer of 163. Boom, done. For this question, we're meant to find f of g of x and then g of f of x. So let's go. Now, when we want f of g of x, we're taking the g of x function and replacing every instance of x in f of x. So check this out. I'm going to put square root of something plus 2. And replacing x, I'm going to plug in g of x, which is x squared plus 3. Now, in this question, they want you to fully simplify it, but we can't simplify it, so we're done. Boom. Let's go to g of f of x. So again, in replacement of x, I'm going to put open parentheses, something squared plus 3. And then wherever there's an x, I'm going to plug in f of x this time. So we're going to have radical x plus 2. Now this one we can simplify a little bit. We can FOIL it out. So again, when we FOIL it, it's going to be rad x plus 2 times itself. So for the first one, rad x times rad x is x. Then we got 2 rad x, 2 rad x. That's going to be 4 rad x. So they're going to combine like terms. And then last but not least, we're going to add a 4 here with that 3 on the outside. Last but not least, combine like terms. So it equals x plus 4 rad x plus 7. Boom, done. For this one, I'm going to start with f of x, which is radical x, but we're plugging g of x into f of x. So check this out. I'm going to replace that x with x plus 1 over x cubed. Now, they want us to fully simplify this, so I can, and check it out. This is how I'm going to do it. I am going to split that radical, which I'm allowed to do, right, if it's a radical of an entire fraction, to say that specific radical of the numerator over that radical of the denominator. And the cube root of x cubed, those just cancel each other out to just become x. So the fully simplified version is the cube root of x plus 1 over x, boom, done. Now for g of f of x, so I'm going to take my g of x function, and wherever there is an x, I'm going to replace it with the cube root of x. So plus 1 over the cube root of x cubed, right? Because I had an x cubed, now I got cube root of x cubed. Again, cube root and cubing are opposite operations, so they cancel each other out. So now we're left with, as a final answer, cube root of x plus 1 over x, boom, done. For this one, I'm going to start by writing f of x, but I'm going to leave this x value blank because that's where we're plugging in our g of x, right? We're taking g of x and replacing each x with that. So I got 1 over would be x, but something minus 4. And then in here, in the parentheses where x was, I'm going to plug in 2 over x plus 4. Now I'm going to simplify, and these parentheses really aren't doing anything, so I can just sort of act as if they're not there. 4 minus 4 is 0, and I'm left with 1 over 2 over x. 1 over 2 over x means the reciprocal of 2 over x, which is x over 2. Boom, done. And for this one, I'm going to take 2 over x, but I'm going to leave it blank for now, plus 4. And I can plug this in 1 over x minus 4, which is my f of x function. I'm replacing x with that. That's what we do when we do g of f of x. Now, again, I can simplify this fraction, right? That's like 2 divided by 1 over x minus 4, which is the same as 2 times the reciprocal of this, which is x minus 4 over 1. I can make that 2 over 1, not that it matters so much, but then we're going to multiply the top. The bottoms are just going to be 1, so it's just, we don't even need a denominator. So then distributing that 2, I have 2x minus 8, and then we still have that plus 4 out there. Last but not least, let's combine like terms. Negative 8 plus 4 is minus 4. There is the answer. Done. Here we want f of g of h of x. So I'm going to do this step by step, and I'm going to start from inside out. So first I want g of h of x, right? So g is normally 1 over x, but Instead of x, I'm plugging h of x in, replacing that x with h of x. I know this is complicated, but here's my h of x, so I'm replacing that x, so it's going to start with 1 over x plus 3. And this part here is just my g of h of x, right? It's just this piece. Then I'm taking g of h of x and I'm plugging it into f, right? That's the last step. So f is x squared plus 1, so I left that x as a blank because we're replacing the x with g of h of x, so that's what's going to go inside here. Now we could simplify it, but it wouldn't really take us anywhere significant, and the answer has it listed like this, so we're going to stop right here. Boom, done. So in this one, first we have to find g of f of x, and again, just to remind you, this is the same as saying g open circle f of x. I just like writing it better this way. So g is negative 3 over x, but I'm replacing the x with f of x, so we got the square root of 2 minus 4x, like so. So now we're talking about the domain of this. Again, we're really talking about domain restriction. So what are the issues here? We cannot have this radical be negative, and since it's in the denominator, it actually can't be 0 either. So whatever's in this radical, 2 minus 4x, it must be greater than 0, meaning positive, and it can't be 0. So now we isolate x, right? Negative 4x is greater than negative 2. I subtract the 2 from both sides, and I'm going to divide by negative 4, divide by negative 4, and I get x is less than, I'm flipping that because we're dividing both sides by negative. We do that if we divide or multiply both sides by negative. X is less than 1/2. So that's the domain. Now we put that in interval notation. So less than 1/2, that means negative infinity is our bottom, going all the way up to, but not including 1/2. So since we're not including 1/2, we put a nice curved parentheses, boom, done. For part A, we're simply taking the quotient of these two functions. So it's 1 over rad x over x squared minus 4. Now to find the domain, we're really talking about domain restriction. So right here, we got a radical x, but it's not only a radical x, it's also in the denominator of 1 over rad x. So there's two problems, right? X cannot be negative because that would take a square root of a negative, and it can't be 0 because it's 1 divided by that. So we're basically excluding all negatives and 0. So we're going to say x has to be greater than 0. And then in this second denominator, right, we got another denominator. This whole thing cannot equal 0 as well. So I'm going to set this equal to 0 for the time being. And then whatever we get when we solve this, those are going to be restrictions as well. So I'm going to factor this as a difference of squares. X minus 2x plus 2 equals 0. This gives me values of 2 and negative 2. So x has to be greater than 0, and it cannot equal 2 or negative 2. Now, this is already accounted for by the fact that we're saying, hey, x is greater than 0. But the 2 we have to account for. So now let's talk about the domain. So it's everything starting at 0, going up to 2, but then we have to exclude 2. So we do a curved parentheses, union, picking right back up at 2, but not including 2. Again, curved parentheses, all the way to infinity. Boom, done. Now for part B, we're going to say P of m of x. So we're going to say P is 1 over square root of x, but in place of the x, I'm going to sub in x squared minus 4, aka m of x. And now, once again, we're going to leave it like this. We're not going to simplify. And my domain is going to be restricted by the fact that this cannot equal 0, and the inside has to be positive. So we're going to say x squared minus 4 must be greater than 0. So we're going to add 4 to both sides. X squared must be greater than 4. We're going to square root both sides. And then we've got x is greater than 2. But when we square root it, we have to remember it's a plus or minus 2. So the positive 2, that's cool. But then it's like for the second solution of negative 2, we have to flip the inequality, or we can write it like this as a compound inequality. So there is our domain from negative 2 to 2. And I'm going to write this up here in interval notation just to give us some more room. So it's everything from negative 2 to 2, boom, done. Last but not least, for part C, we're going to quickly write this up here. This is going to be m of p of x. So I'm replacing that x with p of x, which is 1 over radical x squared, and then it's, of course, minus 4. So I'm going to leave it like this. Now, once again, what are my domain restrictions? Because I can square this and make it 1 over x, but we want to leave it in its pure form to really get those domain restrictions, because we still can't take a square root of a negative. We still can't be dividing by 0. This means that x has to be greater than 0, and if I place that in interval notation, it's simply 0 to infinity, again, not including 0, so the curved parentheses. Boom, done. Write the domain of f of g of x in interval notation. So first, let's write out f of g of x. So I'm literally taking my f of x and I'm replacing x with g of x, which is square root of x minus 1. So we want the domain. There are two things. X minus 1 is in the denominator, so that can't equal 0. And this has to be positive, right? We can't have a negative radical. So I can kind of lump those two restrictions together and say x minus 1 has to be greater than 0. If it wasn't in the denominator, it might be greater than or equal to 0, but since it is, we have the double restriction. And then I just solve. X is greater than 1, right? Add 1 to both sides. Then to put that in interval notation, we're starting at 1, going to infinity again, not including 1, hence the curved parentheses. Boom, done. Here we want f of g of x to equal h of x, which is listed right there. So what I do a lot of times is I like to say, well, f of x can be the big function, g of x can be that inside function. This is just one way to do it. There's multiple ways to do it. But let's say g of x then could be x minus 5. That's what's in the parentheses. And then I can just make f of x x cubed. This works perfectly because if I'm taking f of g of x, I'm plugging this in for x, and I'd get x minus 5 cubed. Hence, these are your answers. Done. For this one, I'm going to keep it nice and simple. I'm going to make that entire denominator g of x. Okay, so we got x plus 2 squared. And then this one, I'm going to make it 4 over x. Now, the reason why this is nice is it's pretty straightforward. When I get f of g of x wanting to equal h of x, what am I doing? I'm plugging g of x in entirely for this x, and I'd get 4 over x plus 2 squared. Hence, these are your functions. Done. Once again, in this example, I'm making my g of x the internal part, which is literally 1 over 2x minus 3. And then nice and simple, I just got cube root of this entire piece. So I'll just make it cube root of x. And then when I take f of g of x, I'm just plugging this in for x. So here are your functions. Done. Here I'm going to make g of x my inside function, right? So it's going to be 3x minus 2 over x plus 5. And then the outside function is just going to be the fourth root of x. This makes it nice and simple because when I take f of g of x, I just plug this in for x and I have the function up here. So these are your winners. Done. Following the trend of the previous problems, again, I'm making g of x this internal piece, which is 2x plus 6. And then we're making f of x the external piece, which is simply square root of whatever we got inside. Let's just make it square root of x. Therefore, f of g of x would bring us back nicely to this. Boom, done. Once again, we're going to make g of x this internal piece, which is x minus 1. And then we're taking f of g of x. So we want the entire thing cube rooted. So I'm just going to make it cube root of x, which would work nicely when we take f of g of x. This whole thing replaces the x. Boom, done. So for this one, I'm going to follow along with the answer provided in the back of the book. But I want to talk about a different answer that kind of makes a little bit more intuitive sense to me. But here we go. For the back of the book, we have 1 over x minus 2. And then up here, we have x cubed. Now, this is very accurate because if I plug this in for x and I cube it, right, 1 cubed is going to stay 1 on top. And then we're going to have x minus 2 cubed on the bottom. No worries. But an alternative way to do this, which I think makes a lot of sense as well, again, looking at this internal piece, I could make g of x simply x minus 2. And then I could have made f of x 1 over x cubed. Again, both are totally acceptable. Boom, done. For this one, I'm going to make g of x, once again, the inside component, which is 2x minus 1 over 3x plus 4. And then f of x is simply the square root of everything. I'll make it square root of x. Now we know if we plug g of x in for x, we'd get the original function. Boom, done. So for this one, we're finding f of g of 1 using the graph. So I always like to go inside out. So first I'm going to find what is g of 1, meaning what is the value of the function g right here when x equals 1. So x equals 1, here's the function value, which is 3. And then I'm going to take f of that value, f of 3. So what is the value of the function f when x equals 3? We go out here. Here's the value. It's 2. So 2 is your winner. Done. Here we're trying to find g of f of 0. So we're going to start with the inside first. So first, what is f of 0? So I say, where's x equals 0? Right here, the function value there is 4. So I'm going to replace f of 0 with 4. And then I want to find g of 4. So 4 is here. That's what is the function value of g when x equals 4. We go up to the function value, which is 5. So 5 is the winner. Done. Here we first find what is f of 4. So here is 4. The value of f there is 0. So now we're taking f of 0. I'm replacing f of 4 with 0 because f of 4 is 0. Then we want what is f of 0. Here's 0. The function value of f at 0 is 4. So the final answer is 4. Boom. Done. Here we're going to find g of 0 first. Like I said, we always go inside out. So g of 0 is the function value of g when x equals 0. So it's right here. And that's 2. And then we need to find g of that value, g of 2. So it's finding the function value of g when x equals 2. So that's right there. The function value is 0. So that's our final answer. 0. Boom. Done. So for this one, we're going to start from the inside out. First, we're going to find f of 2. So what is the function value of f when x equals 2? Here's 2. We go up. The function value right there is 4. So this is now the same as saying, what is g of 4? So now we go to g of x. Find the function value when x equals 4. It's right here. That function value is 2 for the win. Boom. Done. So for this one, we're starting on the inside. What is g of 1? So what is the value of g when x equals 1? Here's x at 1. The function value is 1. So now we're taking f of 1. So what is the function value of f when x equals 1? Here's 1 on the f function. And here's the coordinate, 1, 1. So 1 is our final answer. Done. So for this one, we're going to find f of 2 first, inside out. So what is the function value when x equals 2? So here's that coordinate when x equals 2. The function value is 4. So now we're taking h of 4 because f of 2 is 4. So h of 4, what is the function value of h when x equals 4? So right up here, there's our function value, which is aka the y value. So h of 4 is 4. Boom. Done. Here we're going to start with the most inside part, which is f of negative 2. So we're going to go to the function when x equals negative 2. What's the value of f? It's right here. That is positive 4. So we're going to rewrite this f of g of 4. Then we're going to find the next inside part, which is g of 4. So we're going to go to 4 for function g. There's the point, and the function value is aka the y value, which is 2. So g of 4 is 2. So now we're finding f of 2. So we come back to this graph. Check it out. Here's 2. Here's f of 2, right? And what is the function value at that point? It is 4. So 4 is the winner. Done. For this one, starting on the inside once again. So what is g of 5? So that's what is the function value of g when x equals 5? It's right here. It's 8. So now I can say this is the same as what is f of 8, right? And what is f of 8? It's the function value of f when x equals 8, which is right here. So 9 is the winner. Boom. Done. First, we're going to start with what is f of 3. Here's 3. Here's the function value at 3, which is 8. So now this is like saying, what is g of 8? So here is 8 on the x value. What is the function value of g when x is 8? It's right here, which is 4. Boom. Done. Here we're going to start from the inside. So what is f of 1? So it is the function value of f when x equals 1 right here, which is 6. So then that inside part gets replaced with 6. Now we're trying to find what is f of 6, right? So we find the x value 6. What is the function value of f when x equals 6? It is 2. So 2 is the winner. Done. Here we're starting with the inside, g of 6, meaning what is the function value of g when x equals 6? It is 7. So now we're replacing that inside part with 7. Now we're taking g of 7, meaning what is the function value of g when x equals 7? Well, here's the function value g. It is 3. Boom. Done. So here we want f of g of 2. I'm going to rewrite this as f of g of 2 this way. And it's equivalent, but it helps us see that we're going to go from inside out. So first we're going to find g of 2, right? So here is x equaling 2. What is the function value g when x equals 2? It's negative 3. So I'm going to rewrite this as f of negative 3. So now we need to know what is the function value f when x equals negative 3. It's right here, which is 11. Boom. Done. Again, I'm going to rewrite this as g of f of 3, right? It's identical notation. It's just easier to process the fact that we're first starting with f of 3, the inside part. So f of 3 is the function value of f when x equals 3. That's negative 1. And then we're going to make this g of that inside part of negative 1. So here's -1 for the x value. What is the function value of g when x equals -1? That is 0. Boom, done. So here we're going to rewrite this as f of 3, like so. And again, we're taking the inside first. So what is f of 3, meaning what is the function value of f when x equals 3? It is -1. So I'm going to rewrite this as f of -1, like so. What is the function value of f when x equals -1? It's going to be 7. Boom, done. So first we're finding f of g of 0. Once again, I want to start from inside and then go out. So what is g of 0? Well, I'm going to take that 0 and plug it in to g of x. So that's going to zero out this entire second part. It's going to be 4 minus 0, which is 4. So then this is going to be, what is f of 4? So I'm going to take my 4 and plug it in for x in my f of x function. 4 times 5 is 20 plus 7 is 27. Done. Now let's go the other way. Now if I plug in 0 for f of x, right? 0 times 5 is 0 plus 7 is 7. So this is the same as taking g of 7. So plugging 7 in here, 7 squared, let's write that out. 4 minus 2 times 7 squared. 7 squared is, of course, 49 times 2 is 98. 4 minus 98 is -94. Boom, done. So starting with the inside, starting with g of 0, plugging 0 in for g of x. That's 4 times 0 is 0 plus 3 is 3. So then we're taking that 3 and we're plugging that into f. So 1 over 3 plus 2 is simply 1 over 5. Boom, done. Now we go the other way. Plug 0 in for f of x. So plug it in there. It's 1 over 0 plus 2, which is 1/2. So now we're doing g of 1/2. So now I'm plugging in 1/2 for x. So that is 4 times 1/2 plus 3. 4 times 1/2 is 2 plus 3 is 5. Boom, done. So for this one, we're finding f of g of x, which means we're taking our f function 2 times x squared. And again, I'm leaving a space here. You'll see why. Plus 1. And I'm taking g and I'm plugging it in for every instance of x. So I'm replacing this with 3x plus 5, like so. Now we're going to simplify, even though this is sufficient to some degree, but let's simplify. So 3x plus 5 squared is 3x plus 5 times itself. And then we're going to FOIL 9x squared plus 15x plus 15x, which is 30x plus 25. And all of this is still being multiplied by 2, and we got the 1 at the end. So let's distribute, distribute, distribute. That's 18x squared plus 2 times 30 is 60x, plus 2 times 25 is 50, plus that last 1 will make it 51 for the answer. Boom, done. So here we want g of x. I'm going to rewrite it like so. So what we're basically doing is we're taking our g of x function, which is 3 times x plus 5, and then we're replacing the x with the function itself, which is 3x plus 5. So I'm going to plop that in here like so. Now we're going to distribute, distribute. We got 9x plus 15 plus 5 combined like terms. 9x plus 20. Boom, done. So for this one, we're going to start with f of g of 2, right? So I rewrote it in this format because it's easier to understand the order, because we're just going to start inside first. So first, what is g of 2? That means I'm going to plug 2 in for g of x. That's 2 minus 1, which is 1. What is the cube root of 1? It's simply 1. So now we've got what is f of 1. So I'm going to plug 1 in here. 1 cubed is simply 1 plus 1 is 2. Boom, done. So now we've got g of f of 2. And what I'm going to do is I'm going to start by plugging 2 in for f of x, for x, right? So 2 cubed is 8 plus 1 is 9. So now we've got g of 9. So we're going to take 9 and we're going to plug it in up top here. So 9 minus 1 is 8. So that is the cube root of 8, which is 2 as well. Done. So what is the domain of f of g of x? So let's write this first in this format, and then we've got g of x being plugged into f of x. So that's going to look like this. So then I'm subbing in g of x, which is the cube root of x minus 1. Now, I can simplify, but I want to leave it like this to get the full domain so we don't miss any restrictions. But here's the dealio. Cube roots have no restrictions. I can take a cube root of 0. I can take a cube root of a negative. So there's nothing that's going to cause us any restrictions, which means the domain is all real numbers, negative infinity to infinity. Boom, done. True or false? G of f of x equals big F of x. So let's check it out. G of f of x. So we've got the function g, which is x plus 1. So I'll say something plus 1 because we're replacing the x with f of x, which is x to the fifth. So this simplifies to x to the fifth plus 1. Is this the same as x plus 1 to the fifth? Absolutely not, because this would FOIL out a bunch of times and would be something completely different. So this is false. Boom, done. So first we're finding f of g of 6. So I'm going to go inside first, plug 6 into g of x. So that's 6 minus 2, square root of that. That is the square root of 4, which is 2. That means we're now taking f of 2. So I'm going to plug 2 in for f of x, right? 2 squared is 4 plus 2 is 6. Boom, done. Now we're going the other way, g of f of 6. So first I'm going to find f of 6. So I'm going to plug 6 in for f of x. That's 6 squared, which is 36, plus 2 is 38. So now I'm taking g of 38. So I'm going to plug 38 in for x. That's 38 minus 2, which is 36. Square root of 36 is 6. Boom, done. So we're going to start from inside and then go out. So what is g of 11? I'm going to plug in 11 for g of x. So that's 11 minus 2, which is 9. Square root of 9 is 3. So now I'm taking f of 3. So we're going to plug it in here. 3 squared is 9 plus 2 is 11. Boom, done. And then now we're going to go the other way. So f of 11. So let's plug in 11 first for f of x. So that is 121, right? 11 squared is 121, plus 2 is 123. Now we're going to plug that in for g of x. So that is g of 123, which is the square root of 123 minus 2. 123 minus 2 is 121. Square root of that is 11. Boom, done. The function a of d gives the pain level on a scale of 0 to 10 experienced by a patient with d milligrams of pain-reducing drug in her system. The milligrams of the drug in the patient's system after t minutes is modeled by m of t. Which of the following would you do in order to determine when the patient will be at a pain level of 4? So we want to know when a of whatever we're putting in as the input is going to equal 4, right? Because the output of A, we want that to equal 4 because A gives us the pain level on a scale of 0 to 10. Now, what we're taking as an argument in this function is the amount of milligrams in the system. But this is asking which of the following would you determine when, aka the time, the amount of minutes. So what we're doing is we're plugging in this m function, which gives us the amount based on time units. So we're evaluating this. We're saying, hey, if I know the time, this is going to give me the amount of milligrams left in the system. And then we're taking those amount of milligrams and plugging it into this function a, which takes milligrams as an argument and outputs pain level. And we'd solve this for t, which means that c is the winner. Boom, done. So here we've got a function for the radius as a function of time, right, for a raindrop hitting a lake and the circular ripple. So we want to turn this into an area function, right? Well, what is area? Area is pi r squared, and we're talking about a circle. So now I can plug in this function for the radius and replace r with that. So it's going to be a equals pi times 25 radical t plus 2 squared. Now, if I want to solve for when t equals 2, I'm going to plug and chug. So plug 2 in for t. So 2 plus 2 is, of course, 4. Then the square root of 4 is 2. 2 times 25 is 50. So then we square the 50 and we get 2500 pi. And what are our units? This is in square inches. So square inches. Boom, done. So here we're using the area function from the previous exercise, which is a equals pi times 2t plus 1 squared, because this actually represented the radius. Once again, area of a circle is pi r squared. So now they're giving us a value for t, which is 5, so we plug and chug. Pi times 2 times 5 plus 1 squared. 2 times 5 is 10 plus 1 is 11 squared. 11 squared is of course, 121 pi. And in this case, we can say square units for the unit, and boom, done. Here we're supposed to find the composite function n of t of little t. So we're basically plugging this guy in for every instance of t in this function. So everywhere where I have t up top, I've kind of created a placeholder of parentheses, and now we're going to plug t of t in. So that's going to be 5t plus 1.5, 5t plus 1.5, but we can simplify, but we're going to leave it as is. Now we want to find time when the bacteria count reaches this amount. We're going to use a calculator to do so. And what I'm going to do is I'm going to plug in this value for n, because n represents the number of bacteria. So the way I've chosen to display this in Desmos is I made the first function our composite function, and then I want to know when this function is going to equal 6,752 on the y value. So I said y equals that amount. I'm looking for the intersection, which is right here. And we want that x value, which is really that t value, time. If I round it to the nearest hundredth, it's 3.38. So since t is in hours, it's 3.38 hours. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.